Welcome back to the ARSET training, Transforming Earth Observation Data into Building Infrastructure Data Sets for Disaster Risk Modeling. My name is Brock Blevins, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It is a pleasure to welcome you all to the second part of this three-part webinar series. So a quick recap of this training and why we're here. Why is climate risk assessment important? So even with the drastic reduction in carbon emissions, short and medium-term impacts are inevitable. Climate change impacts and risks are becoming increasingly complex and difficult to manage. Climate change impacts on human infrastructure are not well understood and can vary drastically by location. So understanding community-specific risks to climate change is critical to evaluating adaptation strategies. So here we are in part 2, where we're going to talk about the development of site-specific exposure data with Earth observations. It will once again be a 2-hour part with presentations and a question and answer session at the end. All materials and recordings from each session are available on the training webpage, and there'll be one homework assignment which will be posted on October 10th and will have a due date of October 24th. A certificate of completion will be awarded to those who attend all live parts and complete the homework assignment by the given due date. A little bit on the prerequisites. We talked about having an idea of the fundamentals of remote sensing, basics of GIS and databases, but also the basics on statistics and sampling. Links to each of these trainings are provided, and we encourage you to go through them to familiarize yourself with the content related to this training. Please put your questions in the questions box and we'll address them at the end of the webinar. Feel free to enter your questions as we go, and we'll try to address all questions during the Q&A session. The remainder of the questions will be answered in the Q&A document, which will be posted to the training webpage about a week after the training. So without further ado, I will introduce you to our trainers today. We have Greg Yetman, Associate Director for Geospatial Applications at CIESIN at Columbia University, and Taylar Hauser, Geospatial Data Analyst at Oak Ridge National Laboratory. Greg, you're up first. Thank you very much.
Thanks very much, Brock. It's a pleasure to be here today to talk to you about, first off, working with data to merge building footprints with infrastructure data sets to improve infrastructure data sets for use in HAZUS, the Hazards US package for flood impact analysis. Yeah, so the objectives of this lesson today are to be able to understand the techniques for attributing infrastructure, that is assigning attributes on building details to infrastructure data. Identify issues in this attribute transfer. Specifically, we're going to talk about issues that arise because different spatial models and the difference in locational precision between data sets. Select the right strategies for transferring your attributes, and just by way of how we're talking about different possible sources of data, you should be able to identify common sources of infrastructure data and building footprints. So in 2012, New York State and New York Metro were rocked by Superstorm Sandy. It was a large storm, large hurricane that hit, and you can see some of the photos of flooding and damage across the bottom. And there was a lot of examination of, was New York State, New York City, different agencies prepared for this kind of storm? If this kind of storm hits again in the future, what could we do differently? And what data, key for today, what data are needed for the next storm? What would be really useful for preparation? And it was noted that risk assessment requires more than just population data and building locations, but you need information on vulnerability, building characteristics, population vulnerability as well, although we won't talk about that today, but both are really important for understanding risk and potential impacts. So prior knowledge, some things I'm assuming you know at least a little bit about today would be the basics of geographic information systems. That is that GIS is used to maintain and query spatial data, and it lets you do spatial analysis, that is overlay different layers in, primarily today we're talking about vector space, so where you can overlay layers like building footprints with other layers, tax parcels, or critical infrastructure data, and establish relationships as in which building is inside which parcel or which critical infrastructure point location is closest to which building, and GIS enables all of this. The fundamental nature of vector GIS space is a simple data model of points, which is just a XY coordinate pair for every single point, lines, which are ordered series of XY coordinate pairs, and points are, of course, have no dimension. They're no area, no length. Lines have a length, but no area. They're one-dimensional. And then polygons, like tax parcels or building footprints. You've got a closed series of XY coordinate pairs. And the other key power of GIS is how individual geographic objects, like shown here on the bottom right, the building footprint, are linked to database records. And so on the right, you see this table of the county, municipality, the source of the data, and the roof type, 0 being flat, and the occupancy class, or how the building's used. This is educational class 2. In fact, this is the office building where Juan and I work. This is the building on the campus where we work. So GIS lets you do that kind of query and look up within layers and across layers, which makes it really powerful. And we'll see an example of GIS analysis for transferring attributes from one source to another. So our flood impact analysis, we're using HAZUS, or actually the algorithm from HAZUS, which is short for Hazards US, Hazards United States. And it's an extension to GIS software that lets you do impact analysis for multiple hazards. And in this project, we did it for flood impact analysis. So for flood impact analysis, you need to know the flood depth under different scenarios. This is typically used for planning or preparation, not for post-disaster response. So the flood depths are hypothetical or built on data under different scenarios. And we'll talk a little bit more about the flood scenarios in a bit. And then for your buildings, you need to know information about them, attributes about them, their value, the amount of money the building itself is valued at. The occupancy class, that is it residential, people live there, industrial production, commercial or retail, or commercial also includes service like office buildings, or a mixed use case where you, for instance, have ground floor retail with residential buildings over top. And then institutional, which can be anything from schools through hospitals through churches. And typically, or actually as a requirement for HAZUS, these classes are broken down further. I haven't listed them all here, but residential, for example, goes from residential 1 through residential 9. So 9 different subcategories of residential, things like whether it's an apartment block or a single family home, detached, semi-detached, all those characteristics are in those residential categories. Commercial and industrial are divided into 3 different categories as well. And the institutional is typically sourced by type, a church or a hospital or a school or a university, that sort of thing. And then key for damage during a flood is what's known as the ground floor or first floor elevation. That is not just the elevation of the land at the foundation of the building, but more importantly, what's the lowest point where water can enter? So the sill on a door, how far above ground level is that? Or a windowsill close to ground level or below ground level? Those are key points, or garage door entryway. Those entryways are places where water gets in and causes damage during flooding. So knowing the height or approximate height of that is key for estimating damages. And then critical infrastructure data. So critical infrastructure includes not just buildings, but power plants, power transmission lines, lifelines like key highways. All these things can be analyzed with HAZUS to get an idea of what could be interruptions to service during a flood or other disaster. And today we're going to focus in on the building exposure and attribute in buildings and the building damages, but we also talk about critical infrastructure and transferring information from critical infrastructure from point sources like address lookups to the building footprints. And finally, the flood data we're using in this project are two different sources. We've got FEMA, the US Federal Emergency Management Agency flood data that's modeled, and flood data that was modeled by Stevens Institute for coastal flooding along the Hudson River areas that flood due to storm surge. So key for today is talking about how we compiled this statewide building footprint database. So in New York State, a number of municipalities and counties had building footprint databases, but there was no building footprint data for the whole state. And we're talking about the whole state outside of New York City. New York City maintains its own data. And so we assembled it from multiple sources. We downloaded it online or contacted directly different municipalities and used their databases. We used the Microsoft building footprints, which are footprints that were extracted from high resolution imagery using machine learning techniques. So the footprints were automated and they did have some quality issues. So they required a lot of work to improve the quality and replace bad footprints, fill in missing footprints, things like that. And then we extracted footprints from LiDAR data, open LiDAR data that's available for New York State. New York State Clearinghouse has LiDAR data, and that lets you do a good job of extracting building footprints. We used Esri ArcGIS software and an algorithm they have to extract building footprints, and then reviewed them all and made sure they were valid footprints before we included them. And then as a last resort, the most labor-intensive part was we manually digitized from imagery, optical imagery, high resolution imagery that is available for New York State. We just traced the outlines of the buildings, really roof outlines rather than buildings, because from looking down from above, you can't quite get at the foundation. You're really looking at the roof line, which often overhangs the foundation. So once we had these building footprints all assembled, it was key to have the attributes I talked about that HAZUS requires for using the data in a model. So the critical infrastructure data we compiled from primarily two sources, New York State and the Federal Department of Homeland Security has a national level database. And when we merged the two of them, we still found that there were some omissions and some out-of-date information on the critical infrastructure. So we did some manual collection from municipalities and county websites. So the critical infrastructure all came in as points, not always well-located points. They were typically done by address matching. So somebody enters a street address and a point gets placed at a certain distance along the road based on dividing a street road into segments, a street or a road into segments. And so that has some locational inaccuracies. So we joined the critical infrastructure points to the building footprints just by finding the building footprint that a point fell inside or was closest to. And especially for the footprints that were actually the critical infrastructure points that are outside of building footprint locations, we did validation to make sure that we moved the attributes from the critical infrastructure points to the correct building footprint. And we would use common sources like Google Maps or other online lookups to see if we got the right building footprint for the critical infrastructure. We had to alter our data model partway through because we realized that there were a lot of co-located services in single building footprints. So a fire and police station jointly housed in the same structure. So we couldn't just store fire or police or school or hospital. We had to handle multiple instances of critical infrastructure inside the same building footprint. And we ended up handling this by not adding additional fields, but by concatenating together the different categories inside the field. So in our critical infrastructure field, you can list multiple types of critical infrastructure. They're within one building footprint. And on the right side of this slide is the list of the critical infrastructure facilities that were included in the database. So you can see things that are related to emergency operations, fire, hospital, and response, but also key infrastructure like power plants and wastewater facilities that may be vulnerable during a flood to interruption in operation, and losing power or losing wastewater treatment is an issue for people, being in the dark or not having power that's required for key activities, or the wastewater treatment plant filling can be a problem for potable water, and you may need to issue a boil water order or something like that. So these attributes are key. And then the educational, church, institutional type buildings, they're commonly used for places for people to gather or shelter. So identifying their locations is key as well. So the other thing we needed to do was assign building value and building occupancy class, or the use, to each individual building footprint. So fortunately, we obtained permission to use a statewide building data set on tax parcels. So on the right, you see those bluish purplish polygons that are the tax parcels, and overlaying on top of those are the building footprints that we created. So the tax parcels included the occupancy class for each of the for each of the parcels, and the assessed value of the land, and the assessed value of the building contents, or the building and its contents. Sorry, not its contents, just the building itself. The assessed value for the building and the assessed value for the tax parcel. The land was included in the tax parcels. So we looked at a case where many parcels contain multiple buildings. This was pretty common. It's not shown here, but it's pretty typical for, a tax parcel to have a residential home and a garage that's separate building from the residential home, or a case where you've got something like apartment complexes that are all part of one tax parcel, but there's multiple buildings, or a commercial space, institutional space, where you have one tax parcel for the owner and many, many buildings across it. So in this case, we just divided the assessed value of the buildings across all of the buildings within the tax parcel based on the area of the buildings. Unfortunately, we didn't have complete information on the number of stories, so we couldn't compute volume, because that may have been a slightly better measure of building value, because a 7-story building is obviously worth more than a 1-story building in most cases. But we did use the building area as a way to assign or apportion the value for the tax parcel to the multiple buildings. So that was one issue we had to deal with. And the second one that was pretty common was that many buildings crossed tax parcel boundaries. So buildings were split by tax parcels, and sometimes those splits were because one building or two buildings built side by side with no split in the roof line were recorded as one building. So that's the example you see on this corner, corner to tax parcels, where this building crosses both. And that's just two buildings that are built together with no roof line. So the algorithm to extract the rooftops extracted it as one. So in this case, we would split the building from one into two buildings, and each part of the building would get the value and the occupancy class from the tax parcel that it falls inside. Really common also were issues like this, where these buildings extend beyond the tax parcel. It sort of looks like into the sidewalk or into the street, but really it's just a mismatch in spatial accuracy between the building footprints and the tax parcels. Or buildings slightly cross the tax parcel lines. And again, this is usually due to a spatial misalignment. The tax parcel data were not collected from the same sources, and perhaps not as precise as the building footprints, or vice versa. The building footprints were not as precise as the tax parcels. We didn't have a good way to know which was correct. So we left the buildings where they were, and we transferred the attributes from the tax parcels. After we split the buildings by the tax parcels, we had an algorithm to decide whether that split was a case like here on the corner, where we wanted two buildings, or a case like here where there's just a small part of the building that crosses the parcel line, and that should stay with the original building. And so that algorithm looks like this in GIS. Essentially, we performed an operation called an identity, which is a GIS operation. It's similar to a union or an intersect, but what it does is it splits the building footprints, which is our target data set, by the tax parcels. And if there are parts of the tax parcels that fall outside of the building footprints, they're discarded. So the result is just the building footprints, but split by tax parcel with the tax parcel attributes. We then calculated the area, updated area for each part of the buildings after they've been split as a percent, right? So a percent of the original building area that was split off. So if a building was split into two pieces, each piece would have a percentage of, let's say 90% and 10%. And we ended up selecting small features with a percentage of 20% or less, and merging those back with the original building footprint so that they were not stored as a separate building. And that's the dissolve operation here. And so at the end, you have your buildings with the parcel attributes, a number of which of the buildings have been split into two or more when they cross parcel lines. Other ones that cross parcel lines were reassembled back into the original building footprint and just got the tax parcel attributes from the largest share of area of overlap between the building footprint and the tax parcel, right? So at the end of the day, the tax parcels were not the definitive geography per se. They were what was used to transfer the attributes and split some of the buildings, select set of the buildings into multiple building footprints into multiple building footprints. And so that gives us our complete set of building footprints with assessed value for each building and the occupancy class for each building as well. And so the next thing we had to deal with were some cases in the municipal, the statewide tax parcel database where we had stacked polygons. So here would be condos or co-ops where you had multiple units over each other, right? So in a co-op or a condo, each unit can have its own tax assessment, but geographically they're represented as polygons stacked on top of one another. And so when we were trying to do that relationship between the multiple tax parcels that overlaid with a particular building footprint, that was a problem because we didn't want to take just one of the tax parcel values and occupancy class, although generally occupancy class was the same for all of them, but you could have a condo with ground floor retail, for example. But we didn't want to assign the value from just one part of that to the building. So what we did is for the tax parcel polygons that were stacked or overlaying exactly on top of each other, we created one feature out of those that summed the assessed value and then included the occupancy class or classes, plural, as mixed for that, so that we had just one geometry to transfer attributes for. Yeah. And the second issue we had in attaching attributes to the building footprints were the ground floor elevation or first floor elevation, which I talked about as key for the flood impact assessment process, is generally not available in the building footprint data or the tax parcel data. There's no good database of the ground floor elevation. But the tax parcel data do contain a year built, the year constructed for any structures on the property, right? Whether it's commercial, industrial, or residential building. And we use that to impute the ground floor elevation. And what we did is, if we looked at various building codes for New York State, they changed over time, but they specify a minimum ground floor height or first floor elevation. And depending on the year built, we could look up what the minimum ground floor elevation was according to the building code for the occupancy class of the building. It could vary by commercial, service, or residential, industrial, different first floor elevations. And then we assign that minimum first floor elevation to the structure, depending on the year it was built. So this gives us a good approximation of what the minimum first floor elevation is for all the buildings in the data set. And that we think gives a much more accurate and precise look at flood impacts than a traditional approach in HAZUS, which is to approximate it at the census block or census block group level, where you just have one ground floor elevation height for everything within the same census block or census block group, which is much more generalized. Of course, each building now needs to get the flood depth. And so we used the Federal Emergency Management Agency, FEMA, DFIRMs, or digital flood information maps, for inland areas of New York State, that is riverine flooding. And they published two scenarios, the 500-year flood return period, or 0.2%, and the 100-year, or 1% probability in any given year of a flood. And those have different depths. So we took the digital maps and calculated the depth based on a digital elevation model, and we could then get the maximum depth that each building was exposed to under each flood scenario, right? So we added to each building the flood depth information. And these are key for estimating damages. We then use the HAZUS flood model damage curves. So HAZUS operates inside of Esri's ArcGIS software to do the analysis, but because we were working with millions of building footprints, we actually extracted the flood curves from the HAZUS model and ran it separately in a Python script. It worked much faster for that many building footprints. But on the right, you see 3 damage curves for 3 different categories, one for residential 1, industrial 6, and government 1. And those 3 curves are based on at least, I think, 20 years worth of data that are from recorded floods in the United States, and they would take the depth and the building characteristics, the building type and the first floor elevation, and match it up with the amount of damage that actually happened for the building, and then turn each of those different occupancy class combined with first floor elevation into a curve that would show you the damage as a percentage. And of course, we can take the percentage damage and apply it to the assessed building value and come up with the hypothetical damage to the building in dollars, in US dollars. And so we used each of these curves to look up the damage for every building under both flood scenarios. And in coastal areas, we're using the Stevens data, which still give us flood depths under those 2 scenarios. To assign a building damage in dollars to every building. We haven't released the damages for every building at the building level. What we did is we aggregated it up to census and municipal units so that you could have a total estimate of damage for a given flood scenario for a municipality or a census unit. And the reason we're doing that is that the reliability of the damage estimate for any one particular building in dollars is not perhaps great, because a very small difference in flood depth can make a large difference in the damage impact. So we didn't want to release these numbers as an authoritative estimate of damages under a particular flood for individual buildings. We wanted to look at estimates for planning at the municipal or census level. You can, however, look up in the data online the impact assessment data for individual buildings in categories of damage. So that would be slight, moderate, significant, or actually destroyed is not one of the ones we used. Slight, moderate, or significant damage, and no damage as well as a category. Sorry, I'm mistaken the slide. That was an older nomenclature we had in there. So each of those is assigned to the building footprints. So here's the proper damage categories, right? So individual buildings were categorized into damage categories of none, slight, moderate, or substantial damage for both the 100 and 500-year floods. And you may have learned elsewhere that 100-year flood is not a flood that occurs every 100 years. It's a flood that has a 1% probability of occurring in any given year. So even if a 100-year flood happened last year, there's still a 1% probability it would hit the same area with the same level of flood in the next year. And the same for the 500-year flood, which is 0.2% probability of occurring in any given year. So on the right, you see a table in the bottom right corner to give you an idea of the data that's available. So we've got the county and the municipality, the storm return period, and the building and contents loss in US dollars, and the number of buildings damaged. In each building, we've also got it flagged by whether or not it's critical infrastructure. So you can look at critical infrastructure building footprints and know whether or not it's going to be damaged, slight, moderate, or substantial under both flood scenarios as well. And then finally, attached to each building footprint are recommendations for climate vulnerability. New York State released a report on climate adaptation that included key strategies for reducing flood impact and improving vulnerability. And so what we did is we used a lookup of the building occupancy class for all the buildings that are in potential flood areas and assigned the recommendations from the adaptation report to each of those building footprints. So here's an example for a residential a residential building that's within a model flood zone. Obtain flood insurance, elevate your furnace, water heater, and electrical panel, especially if they're in the basement, right? So it's common for lots of damage to equipment that's in the basement of a home because that's the first place to flood. And you could install check valves, that is valves to stop water from backing up through the sewer. And finally, incorporate flood openings below the ground floor elevation entrance and ensure waterproof building materials below grade so that you can stop the water from entering and give it a place to drain once if it does enter. And then right now I was going to pause and show you a example of the online application that's available. This URL is in the materials for today, but these data have been released as a web mapping application for New York State. So there's a link where you can download all the data, but here we can explore all of the layers that were made available for New York State. So if I click on the Explore button, we'll see at first counties, and it tells us the number of buildings per household at the county level. But once you zoom in, you'll see lots of detail at the building footprint level. So here I've zoomed in on Rockland County and Westchester County and the Hudson River, Lamont Doherty. This is the campus where our offices are. But if I go a little north here into Piermont, we can see some areas of modeled flooding. So this is showing flood depth. The darker the blue, the greater the flood depth for the 500-year scenario in and around Piermont. And so if we zoom in even further, we can see the individual buildings, and you can click on a building and it should pop up in a moment with the attributes for the building. So we see, it actually gave me the flood attributes, should also pop up. It's doing a query here. The service is probably waking up. I'm probably the first one to use it today. I tested it yesterday, but not today. But hopefully it'll pop up. But here it's just showing us the properties of the flood data. But it's always the case with live demos. It's not pulling up the building attributes for me right away. Let me try again and pull up the attributes for the building. There we go. So now it came up right away. So here's the building footprints for Rockland County. The building footprints are served by county. And the general, this is residential 1, which is typically single family home. The imputed first floor elevation, 2.75 feet. And under a 100-year flood, there's no damage in the 100-year flood model. So there's no flood depth or no significant flood depth. Some areas can have very low flood depth modeled, but that would result in no damage. But under a 500-year flood, it would be substantial damage modeled for this. And so we can see the adaptation strategies that are recommended and the sources for those. So you can link to each of the sources for each of the recommendations. And if I zoom out again and we go a little further up the Hudson, we can see, for instance, some areas in South Nyack that see the same thing. Under the 500-year flood, they're shown to be storm impacted. You can choose which layers are visible. So by default, the critical infrastructure is turned off, and both the 100 and the 500-year floods are turned on. I'm going to turn off the 500-year flood And you see a significant difference in the model flood extent between the 100-year and the 500-year. You have to go much further to find something that's potentially impacted by the 500-year, or sorry, the 100-year flood, because the flood depths are so much less. And I can click on that building footprint and see that, oh, sorry, it's returned. I missed the footprint and got the 100-year flood extent. So here we can see that it's actually showing slight damage under 100 and the 500-year category flood. And just to show you what it looks like, here's the critical infrastructure. So each of the buildings is tagged with whether or not it's critical infrastructure. Well, we've added these points so that it stands out more. And if we look at the legend, you can see the types of critical infrastructure that are shown here in the database. A few more than actually I listed on the slides, because I think I overlooked the prisons and libraries as critical infrastructure. And so that's the map viewer that's available, again, for all of New York State. If you're in New York State or you know a place in New York State, you can look up the address and it will get you pretty close to the building footprint. So you could find where you live or where you know somebody who lives in New York State and see if they're within the modeled flood extents. Thanks for listening today. I'm going to hand it over to Taylar Hauser, who's going to talk about using EO data to develop building structures data sets. Thanks again. Taylar?
Thank you, everyone. My name is Taylar Hauser. I'm a geospatial data analyst for the Built Environment Characterization Group at Oak Ridge National Lab. And today I'm going to be talking about the USA Structures Project in a talk titled Using Earth Observations to Develop a Building Structures Dataset. The outline of my talk is pretty simple. I'm going to go over the background and motivation for this work, and then I'm really going to dive into the workflow. And that workflow can be divided into two major parts, from imagery to polygon, and then there's a post-processing workflow where we try to enrich those polygons to correctly relate to the structures with significant attribution. So the driving force behind USA Structures was that in 2016, the United States experienced 32 major disasters, 6 of which involved flooding emergency declarations. And during that time, emergency preparation, response, and mitigation had all been hampered by the lack of accurate current data on the precise location and elevation of buildings. So ORNL proposed a solution that they would build and maintain the nation's first comprehensive inventory of all structures larger than 450 square feet. So this is by no means just my work. There has been a significant amount of contribution over the years. This is a rather long running project since 2017, even though we did some preliminary work in 2016, and it has taken a wide variety of expertise and folks to be able to accomplish this work. So our progress to date it has been going according to plan. We're pretty excited. We just completed phase 2. And in phase 1 is where we really focused on that imagery to polygon. We went through and downloaded images that covered all of the United States and the majority of its territories, and we extracted these buildings. And then phase 2, which we just completed last month, is where we really focused on that latter part, which is where we take that geometry and we enrich it with a lot of attribution to be used in emergency response and damage modeling assessments. So you can see here, these are our total feature counts for each data set that we produce. So over 125 million building detections. And if you want to look at this data or use this data, it is available on FEMA's Geospatial Disaster Platform, accessible by that link on the right. So here's the general workflow for USA Structures. This can be broken down into 3 major parts. The first part is the imagery. When we define an area of interest, we will go and crawl Maxar's data catalog for all of the current imagery, and we'll begin building a mosaic of imagery for that AOI, and that the priority of the images are given to the most recent image with the least amount of cloud cover at the most appropriate viewing angle. And then we'll take that information and we begin building this mosaic. And oftentimes, for example, here in Texas, we ended up with 4,862 images, which is around about 3.7 terabytes of data. And then once we have all of these images, we will pan sharpen them to just under 0.5 meter resolution. And oftentimes that will balloon the data pretty significantly. And for the case of Texas, it ended up being about 44 terabytes of data. That image on the right just shows you the outline of each image that we used. And when the images overlap, we choose the imagery that meets our requirements, our specifications. So the newest image goes on top. Once we have this image mosaic, we will begin developing a convolutional neural network, and we train that neural network to identify building detections and to delineate that building detection in the satellite imagery itself. And we do that by selecting 500 by 500 pixel image chips that we then have analysts go through and manually digitize each building in the image chip. And so we have done this close to 60,000 image chips for the United States. And we have just over 25,000 positive samples. And a positive sample is an image chip that actually has a building in it. And we do also train the neural network to identify when there is no building, and that is when we implement a negative sample. And so that would be a 500 by 500 pixel image chip where there's no building. So for example, a lake or maybe an agricultural field. And this really helps us reduce the false positive rate of the convolutional neural network's output. And then the last part of the workflow is really about taking those polygons, making sure that we validate it, and then enrich it with significant attribution that can be used. So here's the example of some output, the raw output from the convolutional neural network. Just to describe what you're seeing here, you're seeing the actual imagery that was used to delineate the structures, and then the convolutional neural network went through and essentially digitized all of the buildings. So anything that you see in purple is a genuine structure detection. And we're providing examples from Washington to Florida to Pennsylvania to Colorado to show that we are able to do this in a wide variety of geographies, in a wide variety of environments. So we have East Coast, Washington, for example, and East Coast, Florida, for example, and then West Coast, Washington. And we do provide, we're showing Colorado here because oftentimes mountainous terrain is one of the more difficult terrains to extract building features from. So once we have these geometries, we need to find some way to verify and validate this output. After all, this is we're talking about hundreds of millions of geometries, and while we do have a manual QA process, there's no way that we can put eyes on every single structure detection. So a lot of the work that I focus on is how do I develop a model that can evaluate these structure detections, grade them on some sort of quality, and then assign a confidence value to that structure. So I developed the verification and validation model, which is a quality assurance, quality control model that's designed to evaluate vectorized vectorized structure or building detections. Its sole purpose is to identify type 1 error, also known as false positive. And so a false positive in this case is a building detection where there's no building. So this could maybe be a rock or just some sort of polygon that was generated by the neural network that doesn't represent a structure. It is a supervised binary classification ensemble. And for those of you who have a data science background, the actual algorithm that I use is called a gradient boosted decision tree. And here are some of the results of the VVM. I really like this slide because what you're seeing here is you're actually seeing the combination of two machine learning models. We're getting the geometry from the convolutional neural network, and then we're getting the symbology or the color from the verification and validation model. And what that model outputs is a probability from 0 to 100, where 0 means it has a high chance of being a false positive, and 100 means it has a very high chance of being a true positive. And so that's also color coded here. From anything that's red to yellow is considered a false positive, and anything that's that cyan or blue, dark blue color is considered to be a true positive. So this is the way this is how we go through. And even if the convolutional neural network, for some whatever reason, begins generating some false positives, we can quickly identify those and remove them from the output. So for example, on the left side of your screen, there's Campville, Missouri. There's some texture in these agricultural fields that generate a significant amount of false positives. And then our secondary model went through and was able to detect these and automatically remove them. St. Peters, Missouri, in the middle, is an excellent example where both models are in high agreement. The convolutional neural network is generating valid geometries that we expect to represent structures, and the QA/QC model is going through and really being able to verify that these are geometries and they're organized in a way that we would expect them to be organized. So once we've gone through the automated QA process, then we do have some analysts go through and review manually just to make sure everything is working. We always try to have a human in the loop. And then the next step is to go through and to regularize the geometries. And the regularization is just a process of removing non-incident geometries from each polygon to make them a more familiar shape. There are multiple benefits to regularization. Removing so many vertices from each geometry greatly reduces the overall size of the data set itself. After all, we're actually removing the majority of vertices when we do this. So we're talking about billions and billions of vertices that we remove from the data set. It also helps improve the render speeds for GIS software, so it makes it a little bit more user-friendly. And one of probably the most interesting outcomes is that it takes these really jagged polygons, because we're going straight from raster to vector, and it turns them into more familiar shapes. One of our biggest critiques that we got from our sponsors is that the analysts had a hard time trusting this data, even though that we knew it was accurate because we had done all this work. Those shapes that were being produced just weren't familiar, or they didn't meet the expectations of what analysts thought. So regularization is a way to really kind of properly go from that raster pixel space into vector space and have a genuine, nice representation of a structure. There are a couple of drawbacks with regularization. It's computationally expensive. Oftentimes these algorithms can take a very long time to run. And sometimes they can cause difficult to find issues. So if you look at the middle example where the purple polygons are, you'll see that middle polygon has actually been manipulated in a way where it's overlapping two other polygons. And in a building data set, we generally try to not have any overlapping polygons. And we really, if there are neighboring polygons, we'd like for them to be contiguous and not overlapping. And the last drawback is that this is just another complex process to get in between the imagery and the actual output of the actual data set that we're producing. So once we have the geometries, they've been QA'd, they've been regularized, it's not just good enough to say, hey, there's a building here. More often than not, the moment you hand over a data set of buildings, the first question a user is going to ask is, well, what kind of buildings are these? And so we have developed out a schema, and in phase 2, which we just completed, we attempt to tackle this challenge by going through, and we have a rather sophisticated process of trying to assign an occupancy to every single structure in the United States. And so our occupancy domain, it consists of residential, commercial, industrial, agricultural, assembly, nonprofit, government, education, utility and miscellaneous, and then lastly, unclassified. And the way that we go about this is kind of a three-tiered process. The first step is that we go and we collect a lot of geofoundational data from the Highfeld data sets. If you're not familiar with Highfeld, that is Homeland Infrastructure Foundation level data. And they are openly accessible data layers. If you just Google Highfeld open, you'll go there. And we take all of these data sets that they generally have a particular theme that aligns with our occupancy domains. And so we'll do various spatial joins with that data to our USA structures, and we'll derive a use out of that. And then anything that doesn't get labeled by that process, we then move to census housing unit data and lightbox parcel data, where we then intersect any remaining unlabeled buildings with those data sources, and then we try to aggregate or categorize various information from those data sources into our occupancy schema that you see on the right. And then if there's still anything that is remaining that is unlabeled, we then have another machine learning model that can analyze building morphologies. And it'll analyze the building morphology of a various structure, and it'll be able to classify it fairly accurately as either residential or non-residential. So I mentioned building morphologies, and Gauntlet is a tool that I've developed that assists with calculating building morphologies. Gauntlet can generate over 65 various measures, and a building morphology is essentially just a very precise description of the building itself and its physical characteristics, and also its relationship to surrounding buildings themselves. And so Gauntlet is the tool that we use to do this. It'll go through and generate about 65 different measurements. Some of those measurements are very simple measures of geometry like area, perimeter. Some are engineered and they describe a little bit more complex. These are complexity ratio, compactness, roughness, things like that. And then there are also contextual measurements, and these come from spatial point pattern analysis, if you're familiar with that domain, and also scale relationships. And this could be the example of just the number of structures that are surround the one particular building you're trying to describe, or maybe even the pattern of how those buildings are placed within a certain amount of space. And so we calculate all of these building morphologies for each of these structures, and then the res type model will analyze those building morphologies and produce either residential or non-residential. And again, the res type model is only meant to fill a data gap. It's not, we try to rely on the most authoritative data first, and then wherever we have a data gap, then we use this model to fill in those gaps. And the res type model has been trained on labels from parcels. Here's an example of output for the res type model. This is very similar to the verification and validation model that I showed, where it produces a probability, a residential probability. So the lower the residential probability, the more likely it is that that structure or that building detection itself has been labeled or is a non-residential structure, excuse me. And those are here shown in red. As the color gradient gets closer to blue, those are the structures with the higher residential probability. And this is how we go in and fill in data gaps in areas where there's not a lot of rich attribution that can be used to label a structure. So when we finally bring all of this workflow together and all of these models together, we end up with some output that looks like what you see on the right. This is an example of our USA structures data set for Miami-Dade, Florida. And you can see that they've been color-coded by their occupancy class. So any geometry that you see in that dark blue is a residential structure. Anything that you see in purple is a commercial building. Anything that you see in that kind of that green color, that is government. And then orange is education. And you can even see that we have some call outs here where we go through and show off some more attribution that we have for each structure. So for example, if you look at the black box on the right, that's kind of in the middle of the screen, that is pointing to an education building that we know is a pre-K through 12, and we also provide an address when we have available, and then some other characteristics as well. Again, this is all the process of putting through, this is the end product of imagery processing, feature extraction, validating the geometries, regularizing them, and then running them through an attribution workflow that I described. So I believe that is all the time that I have. So thank you for your time and attention. Feel free to email me or ask me questions, and I'll go ahead and hand this back over to Greg. Thank you.
Thanks very much, Taylar. Now I'm going to talk about a second case study for assigning attributes to building footprints, or actually larger areas in this case, not individual footprints. But that is sampling from Google Street View and Google Maps to characterize vulnerability. So for areas without detailed infrastructure inventories, can we estimate vulnerability from samples? Can we look at different regions and some detail in those regions from a sample and characterize the whole region? So by using broad categories from remote sensing classification, and we've seen this with ImageCat doing this approach of image classification, where they take moderate resolution satellite data like Landsat and classify areas into urban core, industrial areas, residential areas, so that you've got polygons that show this extent. So you've got those polygons showing you different areas, different categories. What we can do is draw random locations, draw a random sample of locations from inside of those categories, and then look at the street view coverage to assess vulnerability. And that's the case study I'm going to walk through that we did for Quito in Ecuador. So by the end of the training, hopefully you can understand the techniques we're using for generating a random geographic sample and construct a survey of these components yourself if you want. So we're doing area-based estimates of building vulnerabilities that are relevant for disaster planning. Today I'm going to focus on floods, but this has been used for earthquakes as well. And scoping exercises, deciding where to collect more data. So you could go in, if you're looking at a whole urban area, and do a random sample and decide that some areas are heterogeneous and don't need additional samples, or do need additional samples, and other areas are more homogeneous and don't need additional samples, for example. And this can be used these samples can be used to estimate the prevalence of different vulnerabilities, such as the building type or the average ground floor elevation for flooding, different land use categories. And so the approach is, sort of a survey design where you select your geographic area, select your sample sites, just generating random points, set up a mechanical Turk, and we'll talk about what that is precisely in a bit, and then do your data collection and analysis. So the key thing for survey design, you're doing a geographic survey, but essentially you need to decide what categories of information you want to collect and what options you want to give. So defining your variables. In the table on the right are the variables we collected for the case study in Quito. And we standardized these through a code book so that they became standard options for all of the analysts that were looking at the data. So the code book includes these categories, their names, but also photographs of what each one looks like, so people have a reference to look at. And then we developed a templates task script of the survey variables. So with these variables defined, you can essentially set up a web form so that people can fill it out and for individual sites and quickly assess vulnerability categories across an urban area or even larger areas if you want. So here's an example of Google Street View from randomly selected sites in Quito. And in essence, we take a polygon bounding our area, our case study area. This case, we're doing the whole city, but you could also do a stratified sample by land use type is much more common. And then with your random points, you verify that they're close to buildings, not just in the middle of a field or a park in the city, and drop anything that's not suitable. And then we also ensure that the buildings were included in Google Street View so that you could actually get this perspective view, not just a satellite top-down view of the buildings. And then we set up our Mechanical Turk. So there's two ways to do this. We used an open source software called Local Turk, and it's linked here on the slide, where you can install it locally or you can run it on a server and have multiple people look at the same data. And we exported the remote sensing image that you see at the very top, so a top-down view, and then had a live link to the Google Street View image. So this second image that's showing the Street View, you could pan and zoom and navigate around in Google Street View. Sorry, I skipped ahead a slide by mistake. And then for each site, each randomly selected site, you get a web form. This one's quite detailed. A lot of these surveys could be shorter, but in this case, we're picking out all those variables I showed before. You could select what you think the sill height is, or the first floor elevation as I referred to it. Choose whether the building is detached or a single family home style or standalone building, semi-detached, attached, or it doesn't apply. Enter your number of floors. And then we looked at building condition, status, and material. So the material, masonry or cinder block, wood construction, brick, steel, that's important for earthquake type analysis. But it could be useful to know in general what neighborhoods are mostly made of. And occupancy, if it's available, just whether or not it's occupied, not a land use in this case. The roof type, which is key for hurricane type impacts, and the land use, whether it's residential, commercial, agriculture, industrial, natural, other could include mixed categories. And then we were also, since we're in Quito, which is near the mountains, we're also interested in the street information, what the slope was like, whether it was flat or low slope, medium, or a very steep slope. And for assessing drainage and whether or not there was actually built drainage, sewers and stormwater capture, we were just looking at whether or not there were storm drains visible in the Google Street View imagery and panning around. And then the street cover type, what the street was like and whether or not it had potholes, what the street was covered with and whether or not it had potholes. And note these check boxes, you can check anything that applies. It's not a either or situation where the radio boxes, the round circles, you can only choose one option. And then for some sites, Google Street View didn't work, so we just had that Google Street View not available as a way to drop something from the survey site. So we had to oversample. We had to take more sample points because some of them dropped out because they weren't close to buildings or Street View was not available. So with that, we used Mechanical Turk to collect data for each location. And what we did is we had actual multiple analysts look at the same location. And this is a way of checking consistency and survey design. So if there's certain questions that are where analysts have a lot of confusion, either it's something that's difficult to tell from the Street View imagery, or the question needs to be tweaked or reworded. So we evaluated the data collected for each variable. Here on the right, you see the number of drains, where the brighter colors are more street drains visible from one particular location in Street View. And essentially we found that the downtown core and the more built up areas seem to have more street drains visible, which isn't a big surprise. And then visualize the results in context, like this map we're showing at the right, on the right. So what we found was that flood vulnerability variables for hundreds or even thousands of buildings can be collected quite rapidly once you're set up and running. We've used this approach for other validation techniques and even done something on the order of 10,000 images looked at by 3 separate analysts. That was a much simpler use case than the vulnerability assessment here, but just a 2-question sort of survey, but we found that could be completed again in a day or so by multiple analysts. So it's a really productive way to review a lot of data. But you do need to look at the uncertainty of your output because analysts don't always apply consistent heuristics or rules for deciding which category something falls into. And it's also easy for different analysts to interpret the same set of instructions differently. So examples, especially example images, are quite useful for being consistent. So here on the right is the kappa score, which is a score of the consistency across each of the categories. And so we can see we do quite well in what the building material is, the roof type, the street type, the land use. Less well, especially for the building condition. There's only 54% agreement across the analysts for the building condition. So that's quite a subjective measure. And that might be a case where we've got too many options for the analysts. We might want to simplify that question, or just make sure to provide good examples on what we think the building condition means. So what does poor condition look like? What does excellent condition or good condition look like with photographs, so that it's not so subjective. And then our street topography could be difficult to judge, but we still got close to 80% agreement. The sill height, this is key here, was only 66% agreement. And because sill height is important for any flood impact modeling, if you know the average sill height, you could apply a damage curve and estimate damages from a particular flood depth. But if your sill height isn't being measured consistently, then it's probably not as useful for that type of analysis. So here for the sill height, if we did this again, we might tweak it so that we have fewer categories or broader categories, so that people can be more consistent in their estimates. So that's the data we collected for Quito, the consistency and the reliability. We've got a paper pending on this, so once the paper's out, the data should be released as well, because it's all collected from, there's no privacy concerns with the data. It's just photos that are available from public viewpoints that are stored in streetview. And I wanted to quickly show you what this looks like. So here's an example form. This is running things locally for a particular location. This is inside the US. It's what I had screenshotted before. So here's the two-dimensional satellite view, but the three-dimensional street view, or perspective view street view, is a live interactive type thing. So you can pan around and we could zoom in. So here, for example, if I move down the block, I might be able to zoom in and sort of estimate that, oh, there's 2 steps up, right? It might be difficult to see on the shared Zoom screen, but you can see 2 steps or 3 steps up before you hit the sill for the entry for the doorway, and the windows are the same. So from this view, without being able to see a garage that might have ground level entry, you could estimate it's probably more than a foot before you get to the sill height, or maybe even upwards of 2 feet, right? So the ground floor elevation here would be 2 feet as a category variable. And of course, construction would be brick, single family home. And if we're scrolling around, we can't see any street. Oh yeah, we can see manhole covers. And there's a street drain, for example, right? So we know that there's a stormwater system, probably a wastewater system as well. Yeah, and so this would be a pretty quick way to assess all those questions. So if we go back to the questions, right, we could see that we're looking at a high sill height, it's a detached home. It's just a single family home. I'd say very good condition. We can see it's primarily brick construction. I would say either occupied or can't tell. It looks occupied because the lawn's well cared for and everything, but it's hard to know for sure, but I would probably go with occupied. And if we go back to roof type, looks like it's shingle to me. So, oh yeah, because we're collecting in Quito, it doesn't quite apply to the US case that I pulled up here. Residential land use, flat or low slope, I think. We saw 1 drain and a paved street. I don't think there's any notes to add. And then we could just submit that record and it'll auto advance to the next record, which pops up here. Actually, there's a little bug here. I'm showing the same images, but normally it would auto advance to the next record. And that gets recorded in a spreadsheet that's stored on the computer that's running the local Turk information. So once you're done with the collection from all these points, you've got an ID value for every site, and the attributes recorded in a spreadsheet. And if you run this through for multiple analysts to look at the same site, you've got a way to link things and do comparisons like the kappa calculation I showed you. So that is everything for the second case study. the methods I've shown you today could be used for assessing flood vulnerability or vulnerability for floods, but also different hazards. The key point is you can use some relatively simple open technologies and commercial services that are free to use to rapidly assess vulnerability from different characteristics that you can see in top-down satellite imagery or a street view perspective. So if you're looking, for example, at earthquake vulnerability, you can detect, especially if you're working with an engineer, the primary construction type, which is key for that. Or flood vulnerability, you can see whether or not there's street drainage and what the sill ground floor elevation is, which are key for flood vulnerability. Or you could choose other variables that you think you could see in the Street View imagery. The limiting factor is that Google Street View is not available globally, especially in rural areas. There's very spotty coverage, but it is available for large parts of Latin America and Asia, and of course North America, Western Europe. It's available almost everywhere, but the most rural areas. So you've got a pretty wide collection of data that's updated on a rolling basis by Google that you can use to do rapid assessments. Thanks very much for your time. And Brock, I'm gonna hand it back to you.
Greg, Taylor, thank you very much for those presentations. And I hope the participants found the information very useful in instruction and technique. So let's review what we covered here today. Greg walked us through the methods and techniques for developing a building level exposure data set for a HAZUS flood study in New York City. Taylor showed us using Earth observations to develop a building structure data set. And then we had another case study on using sampling from Street View to characterize vulnerability. We hope that by looking at these case studies and by us highlighting the techniques that were used, that these techniques could be used in other regions. On October 10th, in part 3, the last part of this training series, we'll cover assessing utility and communicating uncertainty. So that'll involve exposure data best practices, developing and understanding the metadata, equity and bias considerations, and another case study assessing climate change impacts with building exposure data in Antigua and Barbuda. Below is the contact information for Greg and Taylor, along with links to the training webpage, social media. And if you enjoyed today's webinar, we hope you sign up for ARSET's listserv to receive notifications on future trainings. Please follow us on Twitter or for other relevant announcements pertaining to NASA's Earth Sciences. We'll now transition to the Q&A portion of today's webinar. Thank you. Thank you, everybody, for submitting your questions so far in this session. So I guess what we'll do is dive right in. If you have other questions, please feel free to continue submitting those in the questions box and we'll try to get to them. And any of the trainers online, if this is a question pertaining to you, feel free to unmute and we can start a conversation. Question 1, HAZUS integrates into ArcGIS, but ArcGIS is not open and not everyone has access. Is there a possibility to look at HAZUS when you don't have access to an ArcGIS installation?
Hey, Brock, I think that's for me. Yeah, HAZUS itself is integrated with ArcGIS, but the software, the algorithms behind it have been implemented as Python scripts that are available as open data. So you can run the algorithms outside of ArcGIS, and the data are also available for download from FEMA directly. So you can get the data and the algorithms and run them. You don't have the advantage of the menu system and the maps and the interactivity that you have in ArcGIS. You also need to know scripting languages, but that is feasible to do it outside of ArcGIS. In fact, when we ran our analysis, we used a Python script for the damage curves.
Great, thank you. It's nice to know that there are other options for the open data. Thank you, and open source software. Question 2, how many critical building infrastructure buildings are high risk? what mitigation approaches are moving forward. And it looks like this referred to the flood study in New York City.
Yeah, the New York State study. We didn't actually calculate the total number of critical infrastructure buildings at risk. I'm not sure why. It seems like an obvious thing to do now that you asked the question. It is there in the data for most of the counties, so we could calculate it. And the recommendations that are being implemented, I don't know the current status. The report has the complete list of recommendations, and NYSERDA, the New York State Energy Research Development Authority, that funded the study, also is funding programs for the implementation of the recommendations. So because a lot of the recommendations are changes in infrastructure, like moving your furnace and moving your electrical panel and locating generators on roofs, they're sort of long-term plans for the changes. I think a lot of newer or even relatively recently constructed critical infrastructure facilities have followed those recommendations when they were built, and it might be the older ones that need to do the updates. So NYSERDA would be the place to check if there's a program for that, but I don't know any other systematic place to look at what's being done.
Thank you, and I'm placing the links to the URLs referenced in the first couple questions, and I'll continue putting those into the chat. But we will have this available for you to download this transcript after we clean it up on the training webpage. Give us about a week to do that, but I just want to, in the meantime, place those in the chat for you to check out. Question 3, does QGIS have damage curve calculation curve methods?
Yeah, as far as I know, there's no built-in algorithm for that, but because the HAZUS methodology and the damage curves are implemented in Python, you could run them from within QGIS. QGIS integrates with Python. It would take some work to adapt the script, but you should be able to, it should be feasible for somebody who knows scripting to do exactly that. Take the QGIS data as input and run the script by providing the correct inputs for the damage curves.
Great, thank you. Question 4. Such a great web GIS application. How do you make a similar flood impact interactive map? Can you please share the repository? So it looks like we're already sparking some interest in trying to replicate some of this work at different locales.
Yeah, so the data are all available. So if you're interested in the data, they're all available for download. But the web mapping application has 2 components, both of which we're using commercial software for, Esri software. So we publish the flood data and the building footprints and the county's critical infrastructure as separate services in ArcGIS Enterprise, used to be known as ArcGIS Server. And then the web application was built with a what's known as a sort of configuration or implementation mode, where Experience Builder lets you build a web application by pointing to the services you want, and even that multiple tabbed interface that we have in the application is available. And then you can configure it. And it is possible to do that without server. If you use ArcGIS Online, you could put services in ArcGIS Online and still use Experience Builder. It's a little more limited, but you can do that. And then finally, I added some notes on if you're interested in doing this with open source software, that you could definitely implement this with the open source equivalents of using GeoServer or MapServer to build to publish the services. And then there's a mix of open source and commercial clients that can do the same sort of thing as Experience Builder. And in fact, you could probably, I didn't think of this when I was typing this out while Taylar was talking, but you could probably do something like Mapbox as an alternative way to show interactive view of these flood data. If there is interest in the code, I think I could, it's not posted anywhere right now, but we could probably make it available, and feel free to follow up. It's, like I said, it was built with Experience Builder, so it's, if you have a license for that, you can look at exactly what we created, repeating exactly what we created with your own data, just through the Esri website or Experience Builder.
Great, and we included your contact information in the slides as well as on this Q&A doc, so you may have people inquiring directly.
Yeah, please do feel free to reach out.
Thank you very much for your time. Question 5, in the section about building footprint detection, I thought I saw that the pan sharpening image is 2.4 ground resolution. Is this detailed enough to complete the building footprint when the building is incomplete by, for example, treetops, or how does the model perform when the buildings are closer together than the pixel size? And I'm not sure, this may be for Taylar's section, just to kind of put this in context. Well, it looks like this maybe was for Taylar Hauser's presentation, and I'll read the answer here. But Taylar had mentioned that he's not able to connect to the audio. But hopefully we can get him back. We're working on a way to get him some audio here and be able to unmute. But in the meantime, I'll answer this. So this is a difficult question to answer, is what he indicated here. Higher resolution does not guarantee higher quality detection. One main drawback of using satellite imagery for feature extraction is trees. Our model will not completely delineate a building that is covered by a tree. It will be a partial detection. We did try to implement leaf off imagery when available. How did the model perform? We found that the view angle of the imagery had the greatest effect. If the buildings were closer together and we had off nadir imagery, the CNN the convolutional neural network would draw both buildings together connected by the facade of one of those buildings. So hopefully this gets to the heart of your question. Question 6. How to select the best machine learning model? As we do have many models available, what I want to do is train the Sentinel images with some drone orthomosaic data I have for building footprint extraction, which that's wonderful. You have some drone data there and you are looking to combine them. And let's see here. Typically, one would select a few different models that are suitable for your needs, then train them all and compare their performances to one another on a validation data set. And when I have a chance, I will put in a link to a training that we had this year on machine learning, really an introductory on using Earth observations. And it's pretty broad, so I think it'd be a good one to check out, and we'll drop the URL on here for you. That was in English and Spanish. Question 7. With object-based classification and supervised classification, I have some good raster data made from drone orthomosaic, but when I want to turn it into a vector, they're simply not good. If you've come across these problems, do you have any suggestions on how to overcome them? And we'll circle back around to that one. Question 8, is the code used to train the convolutional neural network to delineate the building's open access? And yeah, sorry, it looks like that it is not open access, but hopefully some of the instruction there can help you get an idea of how to produce that code for yourself. Question 9, I have a question regarding the rapid advancements in machine learning algorithms for detecting buildings and extracting polygons from Earth observation images. Some of these changes happen quite fast. How do you stay current with the developments, and what criteria do you use to determine when it's necessary to update your models? The answer being we will run a general model first and evaluate the output. If it meets their needs, they will not update. If the output needs improvement, we will update the model via localized training data. Updating the architecture of these models is done every 2 years or so. So hopefully that can be seen as maybe some best practices when working with machine learning. Question 10, can you provide details on the regularization algorithm? Is it available in GIS software and can be run on a PC or a computing server? I also see a reference to Gauntlet, a tool for calculating building morphologies. Is this an open source tool? And can you provide references to such tools, such as scientific publication links, and any details on the res type model? So they're still investigating open source options, but the regularization algorithm that was used was Esri's regularize footprint tool. And I'll drop this in the chat for everybody. All right, question 11. How did you connect the structure in the image to an address in Google Street View or the Mechanical Turk task?
Yeah, I think this is for me. So Street View lets you zoom to a location based on latitude and longitude. So fortunately, we didn't have to get a address to get the Street View link. And the downside is that, you know, if the latitude and longitude aren't relatively close to a street, you'll end up with a blank Street View image. So it doesn't work in every single case.
Great, thank you. I'll clean this up before we post it.
Oh yeah, and I didn't look at this too.
No problem.
I'm trying to catch up the questions. So yeah, I think that on first blush reading that, I think that's true, that you're looking at over the lifetime of a mortgage is definitely a higher probability of flood for question 12 than the probability in any given year. But I think that's more of a issue to consider when looking at homeowners or people that own buildings, whether they're commercial or residential, industrial, whatever, is communicating the understanding that the probability of a flood over the lifetime of a mortgage is relatively high, 1 in 4. Those numbers seem right to me. It would be a factor for investing in flood insurance or remediation adaptation measures for certain. Getting people to realize that.
Great, thank you. Question 13.
Yeah. So
measures built by themselves are a terrible idea. So this is.
I think it's a good idea, and if we could. The reason we're using Street View to estimate is mostly because we don't have access, the resources to go to Quito and measure and other places internationally. And in the US, our New York State example, we didn't measure the sill heights, we imputed them, but mostly it was just there are millions of buildings. So I think it's a good idea though, because we could measure a random sample of sill heights or do a survey and ask homeowners, commercial building owners to measure their sill heights, and then use that as validation data for how well the Street View method works, or for building another kind of model. And in the New York State case for imputing the sill heights, is that a reasonable approach based on a actual measured sample? Would be a great idea.
Great, thank you. Question 14. In the use of HAZUS for flood impact analysis, what do you think the major limitations will be when trying to deploy it for developing countries?
Yeah, I've read, and it seems correct to me that the damage curves being built solely on US data is the biggest limitation, or the biggest source of inaccuracies for impact assessment when you go internationally, right? So the flood depths and the flood models work the same regardless of what country you're in, but the damage curves are going to be quite different. Also, the building construction techniques are quite different. So the damage curves and the engineer's understanding of how the flood impacts work, or any of the hazard impacts work, are largely based on US building codes and US structures. And so different buildings are going to react differently to hazards, whether it's flood or or other HAZUS models, just because they're built differently. So they might be more resilient or less resilient, more susceptible to damage or less susceptible to damage, and that's not really captured in the HAZUS model or data because it's all based on the US. And then there's some technical things like the HAZUS data are based on, some of the HAZUS data are based on US Census measures at the block or block group level. So those measures may not exist or may be slightly different internationally. So you'd have to adapt them to fit.
Okay, great. So a very local specific inputs are needed there, of course.
Yeah. In fact, there's case studies where HAZUS doesn't work well for exceptional cases inside the US. For example, New York City, the original version of HAZUS, they may have updated this, but it couldn't model a school that wasn't on the ground floor. But if you're in New York City or some other large cities, you'll have schools that are on the second or third floor of a larger building. And a school is a lifeline or a critical facility that didn't exist in the world of HAZUS, to take one example.
Do you know, for those exceptional locations, even in the US, where the model doesn't capture it correctly, do you know if there's any documentation on methods that people used to get around that?
I can check. I don't know off the top of my head. I know there was, I know that from talking to folks in New York City Office of Emergency Management, when they went and applied it for New York City, they found that to be an issue. And I believe they worked around it, so it should be documented somewhere, and I can do some digging and see, and post it for the follow-up.
Thank you. Question 15, how can we automate the process in Google Street View using computer vision like the floors? Additionally, it would be useful where we have a dense, homogeneous urban environment.
Yeah, I think this has been done. In fact, I think Google may itself use computer vision and Street View data to do some of these extractions, just from having chatted with a few folks. We haven't tried it. I think our biggest issue in Street View is that in the areas we were sampling, there was a lot of not heterogeneous environments. So Street View wouldn't necessarily, the URLs were generating, you had to pan around just to find the building, the right view. So automating that process, I don't know how to automate finding the front of the building in Street View, though it may be possible. So logistically, it just seemed, or technically, it just seemed too challenging for our use case, like the exurban or suburbs of Quito, and we worked in international states. But if you're doing an urban core, it's probably much more feasible.
Great, thank you. Question 16, how do you distinguish between single family dwellings and apartments? Shouldn't LiDAR data give you some hint of the building heights, at least enough to distinguish high-rise apartments from two-story single-family houses?
I'm not sure if this is for me or for Taylar. But in our New York State study, we were distinguishing the building type just based on we had the New York State parcel information, which would tell us the building type. LiDAR data can give you, if it's good enough detail, give you definitely the height of a building. And you could, not to put words in Taylor's mouth, but you could definitely infer whether or not it's likely to be a single family home versus apartment building based on the height, though it would be wrong probably in some cases.
Great, thank you. Question 17, this seems to be the last one on here. If there's any others, please feel free to jump on in. But this is the third example of the case study output available to the public. Where can we see more of its visual results?
Yeah, so we haven't published the data yet. We have a paper in review or under draft, I forget the exact status. So we're waiting for the paper to be finalized in part 2 because there may be revisions to the data based on reviews of the paper and feedback on the paper. So it will be published, hopefully on our website sometime in the next 6 months. But feel free to reach out if you have particular cases. I have some images I could share of the results for sure. Even before it's published.
Great, thank you. Appreciate that offer. and look for the publication to come out in the next couple months. You said on your web page, do you mean the CDAC web page?
Yes, yes.
Okay, thank you. Question 18. Could you tell us more about any other web app optimization problems you solved besides regularization? Once again, this could be for Taylar. I'm trying to determine.
Yeah. I mean, I can talk about the the web app, the data service optimization we did for the New York State. I don't know if it's relevant or not, but a lot of it had to do with there's a large number of buildings in New York State, so we had to tune the performance to serve the buildings. And what we did is use tiles. So we built tiles for the flood image data and tiles, vector tiles for the building footprints. So when you're looking at those data, in a large area, you're getting a reduced resolution version of the data, so a much smaller, lighter version of the data. And then when you query or click on the map, it's actually throwing the query for the data details to a different service endpoint. So the visualization is simplified and has no attributes. But when you click on the map and you're requesting details, it goes back and looks for that individual feature or the pixel in the flood depth raster and sends that information based on a query service. So it doesn't have to serve as much data. So that was a big optimization thing. And those are pretty standard approaches for web map tuning.
Great. Question 19 and 20, both referring to sill heights. Building insurance sill height info available? Or?
Oh, that's a really good question. When we were assessing the sill heights internationally, we didn't have, I don't think there's a lot of insurance on information. I don't know if that's collected inside the US by insurance companies. I would be surprised if they did, just from my own experience buying house insurance. Nobody's ever asked for the sill height. They may impute it like we did based on building codes or the age and the age of the house, or maybe they're not doing models that detailed. I don't know. From talking to different folks who do this kind of damage modeling for the insurance industry, a lot of that algorithm and data that they have is considered proprietary. So if they do collect it, it's likely not in an open database or a way we can access it.
That makes sense, yes. Question 20, how sensitive are the results to the precision of the measurements? For example, are sill heights sensitive at the inch or foot or yard?
Yeah, I think the sill heights are more likely to be sensitive or accurate within a foot or so, definitely not an inch. And it's going to vary a lot with the individual building and how close the street view imagery will let you zoom in. So the example I showed in the live demo, you could make out that there were 2 steps and then the door sill above the 2 steps. So, in building codes in the US, you could probably look up what the standard height for stairs are, but it may vary from that. But, you could count on those being around 8 or 10 inches steps and then add a little bit for the sill heights. So you can be pretty confident it's over a foot and likely closer to 2 feet, but I wouldn't say it's anything more precise than that. And then for other buildings, you just don't have a good idea because it's the imagery isn't detailed enough. So it's maybe only accurate to closer to a yard than a foot.
Great, thank you.
Sure. The other thing I just want to throw in there too is that the street view imagery only shows you what's visible from the street. So if there's if in the back of the house or the side of the house there's lower entry points, you wouldn't see those, so you wouldn't know the actual minimum sill height from for the whole building. You're just sort of estimating from the front of it. And in the New York State case where we were imputing from building codes, the assumption there is that the buildings were constructed to code and inspected and passed and not modified subsequently to either have a better sill height, higher sill height, or a new entry point that's lower.
Great, thank you. Question 21. Regarding characterizing vulnerability using Google Street View, was the data mechanical Turk etc., later used to categorize the region into different levels of vulnerability? If so, could you please describe this further or demonstrate this?
This is actually ongoing work. We don't have anything complete yet for different regions. So I don't have anything right now to show, but we do hope to do exactly that. Take the random samples for a place like Quito and merge it with the characterization of the neighborhood for moderate resolution remote sensing data, like the approach ImageCat has done, where they characterize urban areas based on, industrial or large or high density residential, medium density residential, low density residential. And so based on the sample points inside those different categories, hopefully we could say something about the average or the representative sample vulnerability characteristics. We've actually collected data from more cities internationally, but that's, like I said, it's ongoing work.
Great. Thank you. And that seems to be the last question. I think that we will close this out here. I just wanted to give you if a chance, if there's any parting words that you would like to say before we sign off here today. You gave a great summary within your presentation, but just wanted to see if there's any additional comments you want to make.
Oh gosh, thanks for the time and the great questions. These really made me think. So it's nice to know people are interested and have some really probing questions that it's actually useful to hear these and think of new ideas, like extracting, automating the extraction of things from streetview. It's something we should investigate and see if it's been done, because it could be really useful.
Great, yeah. I hope this presentation sparks some conversations and help form a community, all working towards very similar outcomes. So yeah, also we will be distributing a survey after this training is over, and that's another way that we can hear from you some things that maybe you're working on in your area, or things that you'd like to see in the future from us, the ARSET program, CDAC, or ImageCat, or the community working on this disaster risk modeling. Okay, well, I guess we will shut it down for today. We hope that you all will join us for part 3 on next Tuesday. So thank you very much, and I hope you enjoy the rest of your day. Thank you very much.